Good evening, everyone. This is Dawn. On behalf of ASQ Toronto section, I'd like to welcome you all to this webinar and invite you to join us for online learning opportunities via ASQ Toronto section webinars. Please note that this webinar is recorded and recording will be available on ASQ Toronto website as well as ASQ Toronto YouTube channel. Also, there will be 5 to 10 minutes time after the presentation for questions and answers. Please post your questions on the Q&A section of the WebEx tool. You will be given 0.1 RU recertification unit for attending this webinar if you attend 40 minutes or more and filling out the survey. The survey will be sent to you after the webinar session. The topic of this webinar is Disruptive Analytics in Quality 4. There is much discussion these days about disruptive technology. Cell phones replacing landlines, electronic fuel injection replacing carburetors, and the calculator replaced the slide rule. What about analytics? Do elementary schools still use flashcards for students to memorize timetables? Data warehouses in memory computing, streaming data from connected devices, and high-speed analytics are all available to quality and Six Sigma professionals for their projects. In this presentation, some analytical tools are described in detail, while others summarized to show their disruptive nature. The learning objectives are evaluate methods for analyzing high-volume, high-velocity data versus low-volume, low-velocity data. Recognize the proper methods to analyze data at rest, data in motion, and analytics at the edge. Understand the importance of machine learning for predictive models. Recognize the importance of working with information technology, IT, and operational technology, OT, to acquire the best analytical software. Now, I'd like to welcome our presenter, Jim Duarte. Thank you, Jim, for accepting to be our speaker. Jim Duarte is a fellow of ASQ as well as being certified as a quality engineer and Six Sigma Black Belt, who also holds certification as a Lean Six Sigma Master Black Belt. During his career, he worked as a biostatistician in clinical research, pharmaceutical quality, electronics manufacturing, heavy industry, and healthcare. He worked as Director of Technology in Corporate Quality Assurance at Reynolds Metals, Director of Strategic Business Analytics at Anheuser-Busch, and a Senior Consulting Manager at the American Productivity and Quality Center. His current research is dedicated to Internet of Things, IoT, Big Data, and Disruptive Analytics. His teaching activities include ad hoc professor at Washington University, California State University, Sacramento, Webster University, National University, and University of Wisconsin Parkside. He has numerous publications in the areas of statistics, process improvement, and strategic planning. He possesses 5 patents for analytical methods, which include 2 in the U.S. and 3 international patents, with another still pending. Now, I would like to hand over to Jim Duarte. Jim, please take it away.
Thank you very much for that introduction. I'm pleased to be here tonight and honored to be on your program this evening. I'm looking to see if you are seeing my screen.
Yes, your screen is shared.
Oh, good. Okay, we'll be talking about disruptive analytics, and I guess one of the big things is my disruptive nature in the quality field. I started on this journey over 10 years ago, attempting to get papers on this topic at conferences many years ago. And I kept being told that it wasn't quality and it wasn't Six Sigma. And basically, they told me to go away. In the fall of 2016, the innovation division of ASQ accepted my paper along these topics and that opened basically the floodgates. I spoke at several conferences in 2017 and also in 2018, and I'll be speaking with teaching with Dr. Kano in Taiwan in June, which is going to be a very big thrill to me. But this disruptive work that I've been on the road talking about is really near and dear to my heart. So if we look at industrial disruptions, the former chairman of and CEO of GE, a big Six Sigma company, talked about the fact that you might start out as a manufacturing company in industry one day and wake up the next morning being in software and analytics. So even GE recognized the fact that the landscape was changing. 21st century Kanban. When we think about putting out a Kanban card to receive parts or receive things, if we think about Amazon Prime, we as a consumer are actually putting out something analogous to a Kanban card to have things delivered to us. And this, what's called Amazon effect, has really wreaked havoc on brick and mortar shopping. Several companies have closed many stores all over the world because of online shopping and things like the Amazon effect. So there's disruption there in our society. Progressive disruptive technology, as Don mentioned in my introduction, is the progressive nature of when I was in grade school, we used flashcards to memorize multiplication tables. Then I was a geek that carried a slide rule around college, then got a calculator, and then moved through mini computers and PCs. So quality professionals, really, if we look at it and think of it disruptively, are more than inspectors. You're more than policy enforcers. You're more than just documentation experts. And you're more than just quality estimators. So really, when you look at the potential of a quality professional in disrupting the thought process around what quality people do, you do a lot more than these functions, but sometimes we get pigeonholed into these types of activities. So moving forward then, I've coined a term called Imaginalytics. It's combining your imagination with analytics. And I've been lucky as an individual. I am a right brain analytic. I'm very creative. I have many creative things. I use my imagination a lot. I've been very good in design of experiments because I can picture systems and then apply the formulas for analysis of variance and other types of tools. So we need to combine our imagination with analytics to disrupt and break out of the quality paradigm that people have for us. So let's use your imagination. Have you thought about using FMEA for lost contracts, lost customers, or lost employees? So looking at your failure modes and events in these areas. You can also look at survival analysis. If you think about a light bulb works until it fails, so it works until it doesn't. If you think about a customer, you have a customer until you don't. And you can use survival analysis and hazard plots to look at the length of time you've had customers, the length of time you've had contracts, and analyze things along those lines and help other departments in your company. Designed for failure modes and analysis. Have you ever thought of using that in helping marketing with a new ad campaign and finding what the failure modes are in an advertising campaign and helping a marketing department? Control charting sales and revenue. Those things are talked about in Don Wheeler's book on man-made chaos. Very interesting when you're control charting sales patterns. Predictive modeling for who might not pay, minimizing bad debt ratios. So for example, working with the finance department to build predictive models to see who is likely to pay and who's likely not to pay their bills and at what rate, and helping the finance department. The big thing that we have going for us as quality professionals with our tools is we can help minimize false positives and false negatives. With the right kind of statistics and modeling, we can reduce false positives and false negatives through our analytical techniques that we know as quality professionals. So use your imagination and see where you can expand your career into other areas because you have all of these tools at your disposal. Here's a manufacturing company of appliances, and they talk about using near real-time warranty data on connected appliances. Yes, there are appliances out there that you could actually get your email on. I don't want to get my email on the face of my refrigerator, but it's possible now. And what they're using that data for is to give information to their service representatives prior to the call. So when we start looking at the ability of taking information from connected devices, not only can we take it individually for a service call, but collectively, and looking at that data to help better the quality of appliances and other types of things that we can get data from. So now, let's look at the data that we have. There's discrete and streaming processes. Discrete is basically make one, move one. Could be very fast, could be the bottling line at a beverage company, or it could be slow like making an automobile. But basically what we need to do is we need to look at the velocity of not only the data, but the velocity of the process. How fast is the process moving? How fast is the data coming to us? And what can we do to harness that data? So when we look at the velocity of the process, if we're talking about an operating room in a hospital, the process is slow, but the data is coming fast from the patient's vital signs. So there we have a slow process and fast data. In the picture here, we have a bottling line where not only is the process fast, but the data is also fast. So we need to evaluate what we have with our data. And in a lot of cases, sampling is just not going to make it. What's the volume of the data? What's the volume of the production and the volume of data that we're getting out of that process? How much data are we getting? Now with technology and data warehouses and data lakes, we can handle large volumes of data and analyze all of it. We don't need to cut back and sample in many cases. So sampling, which I took a whole course on in graduate school, is becoming somewhat obsolete. And then there's the variety of the data. How many variables can you handle? And how much data, what's the variety of the data and the type of data that you've got? If you look at the picture of the truck, that truck is connected, and all of the things about that truck and its performance can be downloaded and used also not only for evaluating that individual truck, but that data can be aggregated and used by engineers in design for Six Sigma. So we have all this data that is coming at high speeds, high volumes, and with a lot of variety. So if we look at manufacturing, for example, and it's connected, we've got robotics, we've got printing, we've got electronics, we've got packaging, high-speed lines that give us sensor data that we can use then to feedback and look at the quality of not only the product, but the processes. If we go back here, notice the subtitle on this slide, leading versus lagging indicators. The lagging indicators are your measures on your product. The leading indicators are all the measures that you're getting off these sensors in places like manufacturing, healthcare, in operating rooms, hospital pharmacies. Notice this hospital pharmacy has a robot that's actually picking out the prescriptions for this large medical center. ICUs, significant amounts of data coming off of patients. Electronic medical records, and we'll talk about text analytics in a few minutes and how we can handle that. Then there's process industries. In utilities, smart meters will give you a lot of information and can give feedback back to customers about the best time to use a washing machine or a dryer to be off load and actually help their bill and help the electric company. The electric company can use that data to plan for future building of new facilities. Oil and gas. One of my patents is on a drilling process where we're taking data and geological data and analyzing when the geology changes to help the drillers on the rate at which they are drilling and pushing the drill down. A broken drill head half a mile below the earth is very expensive to fix. Liquids, fill lines, and then chemicals. All these areas have historian databases that you can mine and sensor data that you can track. The interesting thing here to think about in all these cases is ineffective maintenance costs about $60 billion a year. So not only can we look at the quality of the products and the processes, we can also look at the reliability of not only the products, but the reliability of the machines and preventive maintenance. Something that I've coined just recently, that quality professionals possess more analytical tools and expertise than most employees. Sharing these talents will provide better insights on all processes in an enterprise for better decision making. This is where the quality professional really needs to be disruptive and know when to put their talents to work, because decision making is very important. One of the key things to look at here is collaboration. Processes and engineers create good data. Machines, materials, operating parameters, information technology, operational technology, IT being the administrative side and sometimes the only one in a company. But if you're big enough, you have OT, where you have actually a computer group that works with your robotics. They have access to the data. So you have it created, you have a group that can access it. Now you need a group to analyze it. And this is where the quality people come in, is in the analysis. But you can't do analysis if you don't have good data created and have good access to that data. Several papers that I've seen at conferences recently are the fact that the biggest problem in doing data science is getting access to data. For some reason, IT and OT people act like a bad union and don't want to give you access to what they have. This is a key slide for senior management to see, because I've worked for a software company and seen their sales process. And their sales process is to go to senior managers, show them glitzy, cool stuff to make a sale. When in fact, then the data science people, the quality people get left out of the decision making, and you get a product that may not fit your needs. Senior management needs to look at the creation of the data, its integration with the access to the data, and integrating that to the analysis of the data. This is a key concept that senior managers need to look at, and look at the big picture to make sure that the money they spend on analytical software and other software meets the needs of all three categories. So when we look at the new era for quality, Industry 4.0, Manufacturing 4.0, Smart Manufacturing, Quality 4.0, we have sensors and machines, computers, big data and advanced analytics. Translating that into good decision making is the key. And then we also must have secure and trusted communications. One of the things I'm working on for my next set of presentations is using Dr. Kano's matrices for looking at cybersecurity. Tonight we're going to just focus on these two points on the analytics and decision making. So I proposed 7 newer tools for quality professionals. And these are the 7 tools I proposed. I presented this at the World Conference last month in Seattle, and it went over really pretty well. I had 3 requests for me to write a book on this. So if we look at text analytics first as one of the new tools, disrupting surveys. If you look at surveys, and if you need a survey to be scientific and all that, that's fine. But if you don't, the thing to remember is the response rate. So if we look at the response rate, let's say we send out 100 surveys, and the question is, should ASQ continue pursuing Quality 4.0 with a response of yes or no? So if we send out 100 and ask that question, and we get 50% response rate, if half the people respond and 37 are yeses and 13 are nos, we're really excited. We've got 74% of the people that say, yes, we should continue to pursue it. But what if the other 50 who didn't respond would have said no? We have a totally different result by our sampling and in our survey. So we need to be careful when we start looking at surveys and start looking at response rate to see if in fact the response rate will give us the same result if we had this kind of a result from those who did not respond. So if we go to text analytics and we look at the voice of the customer, we can do things like word clouds. And word clouds count words. So we can take a document and we can count the words and see what's the most common word that comes out of a document. And we can do these word clouds. These can be done in Microsoft Word. So MS Word has the capability of doing word counts. And you can also select out words that you don't want to have, and you can start paring down things like the, this, that, and take those out and get down to the heart of the issue, but it's still only a word count. And I say only, and you'll see why in a minute. You could also do text mining and do concept links where things like brake failures can be looked at in various ways, and what are things that are associated with brakes, with skids, with parking. Different kinds of things can be looked at in concept links in text mining, and you can get some relational information that way. Then there are dendrograms where you can get different kinds of clustering and information and how it groups together. So grouping of words and phrases. One company that was delivering pizzas was getting all kinds of information off of their surveys, but they weren't sure exactly why customers were disappointed. So they were making great pizzas, but the delivered pizzas were not what customers wanted. The delivery process had a problem, and their surveys were slow and not giving them the information. So they went to social media. And looking at social media, they found out that, oh, there's a failure. Look at that pizza slid against the wall of the box. So they looked at the delivery process. This was in a foreign country where delivery was done or is done on motorbikes. And what they found was, and for those of us who've ridden motorcycles, when you take a turn, you lean. And what they found out was when the operator leaned, they got this kind of a failure on their pizzas. So by using social media, they found more information, actually had pictures to see what it was that the complaints were about. And so they built into their scooters a mechanism to keep the box parallel to the horizon, similar to a stove on a ship or a boat. So now they were able to fix the problem by having more information in a faster fashion than with surveys. So now another big thing in text analytics is disambiguation. Paris Hilton walked into the Paris Hilton. How are we going to look at what the important pieces of those are? Okay, word count. Paris is there twice. That doesn't tell us anything. Paris Hilton is there twice. That doesn't tell us anything. Paris Hilton walked. Okay, that's a person, and the other one is an object. How do we know that? Back in 1985, Stanford University created their linguistics lab. The first class required of all students in the program was sentence diagramming, something that I did back in 7th grade, and I don't know about you, but I thought, when am I ever going to use this? But sentence diagramming takes the subject, the predicate, and the modifiers. And so by using sentence diagramming and that whole concept, they've now written machine learning algorithms that do this to disambiguate text so that we can now see text in a way that is more meaningful than just word counts. Machine learning. Human learning, this looks like me back when I was doing my master's thesis. There's the cards for a simple regression program. Just kidding. not really. But it gives you an idea of what we went through in human learning, trying to iterate through algorithms manually. So now machine learning on supervised and unsupervised analysis. Supervised meaning you have a predictor variable. Unsupervised means you're just doing things like looking through the data and exploratory data analysis. So unsupervised is exploratory, supervised is predictive. So when you're doing machine learning, three key pieces are that it's iterative. So that iteration I showed you manually is now done automatically, and even you have automatic imputation schemes to impute missing values. You have automatic transformation suggestions, like is your data really exponentially distributed or log normal? You have these automatic things. And then the key part of machine learning is predictive accuracy over model elegance. I know back when I was doing my master's thesis, all I cared about was R squared. What's the R squared on my model? Well, we know that R squared can often be high and create an overfit. So that's why there's the use of holdout sets to minimize overfitting. So what is a holdout set for those of you who may not know? That's when you take your original data set and you sample out some testing data. So you take the bulk of the data and build a model, and then you take the testing data that you've held out because you know what the results are, and you plug it back in and see how accurate your model is, and you iterate through that until you minimize the error. Some software actually holds out 2 sets and tests twice. So the machine learning algorithm then goes through this process until it comes out with a final model that is the best predictive model, often called the champion model. Neural networks or machine learning, I have studied these and I kind of understand what they do, but they're very intricate but very interesting because they work the way the human brain does, and they're fascinating. We're not going to go into detail here, but neural networks is a machine learning tool. Decision trees are very interesting. There are several algorithms out there that different software packages use, but the key here is, and it's at the bottom of the diagram there, it says the biggest benefit is it finds the optimum interaction through AND logic. If you think about it, and I've gotten a 100% yes answer to this question. Have you ever had an event occur and no alerts went off? And 100% of the answers have been yes, that's happened. That's because alerts are set up with OR logic. This alert went off, or the next alert went off, or the next alert went off. When in fact, we really want to use AND logic, which says this happened at this level, and this happened at this level, and this happened at this level, and this happened at this level to get us to this point. With this interaction then, is that a new alert? And the nice thing about that is when you take the rules behind that key node that is very important to your decision making, you can take that rule and add it to the rules you have, for example, for control charting. So we have the Western Electric rules that we've used for decades, but now we can add to those rules by taking rules out of a decision tree and taking those interactions, that AND logic, and we can supplement our control charting and other types of analytical methodologies. Predictive modeling. In a streaming ecosystem, first you can create the model. That's done by taking data at rest, data sitting in a data warehouse or a database, and you can create a model. You get that model created, and then with analytics in motion, you can actually put data against that model and look for signals from random noise and be alerted. So it goes back to control charting. When you've got special cause or common cause. So as the data is coming in, there's always some variability. But then when there's an out of control point or a signal, predictive models can take that data and give you the probability. So for example, if you have a credit card, you've probably been called at some point in time asking you if a certain purchase is valid or not. That's a signal. So they look at your data, and with just random noise on your purchases, what are your average purchases and what's the boundaries on your purchases, they see something that's not right, it sends a signal, and that's an alert to contact you. So that's the use of the data in motion from your purchases. Then there's analytics at the edge where you can deploy this. The best example that I've thought of so far is electronic fuel injection in your car. The data is used at rest to build a model on the most fuel efficient use of the electronic fuel injection, taking all the variables into account of your speed, your RPMs, and all those things in your car. Then in motion, that data is used by the car to analyze what's going on and what it should do to make sure that your car is running at the most efficient peak. So that's the data in motion. Then what the companies have done is they burn a chip, and that chip goes into your car at the edge, and let's at the edge, and it actually takes the data in your car and runs it through a predictive model that is now optimizing your fuel usage, so your electronic fuel injection. So I found this is a very interesting example, one that most people can relate to in creating the model from historical data, using it to best find the fuel efficiency, and then building a chip that can be embedded in the car so that the car uses that information to give you the best mileage. So if you're going to do predictive modeling and inequality, some basic steps are to access the data. And a key here in number 2 is end-to-end in the process. This is something we're now able to do because we can get the volume and the variety of the data from the previous slide. We can take high volume data with high variety and process it and perform modeling analytics, get the key variables out and apply those. Notice the bullets under number 5. Redesigning a DOE using key contributing variables. The first question you should ask yourself before you do a designed experiment is, do I have the right variables? And as Dr. Deming would ask, how would you know? So oftentimes running a predictive model first will find the key variables and make your DOE much more productive. You could also determine the critical few variables for control charting. So instead of having control charting on every variable in the process, you can actually narrow that down with predictive modeling to find out what are the variables that have the highest contribution of importance and information to your process and focus on those control charts. You may have many that don't really give you a whole lot of information, and you may not want to have to do control charting on everything, but the key ones to your process that you found through the paring down of variables with predictive models. Here's an example. Coating coming off of an anodized piece of cookware. The pan is dipped in an anodizing bath, so it goes in silver, comes out colored after it's been anodized with the coating put on it. A DOE was run, and these are the variables that were used: acid concentration, soak time, bath temperature, voltage. So a DOE was run focusing on the anodizing process to help see if we could reduce the amount of peeling. Well, those were the variables. And then the results that came out of the DOE is to minimize the peel percent. So percent peel was the variable that we were trying to predict. And what we found was low temperature and high voltage did minimize the percent peeling, but peeling still remained, but at a little lower level. So we didn't solve the problem with the DOE. So we went up to the beginning of the process with the rolling of the plate that's used to make the pan. So again here, the key is end to end. So we went all the way up to the beginning of the process, the rolling of the plate, to see what variables in the rolling of the plate before it was made into a pan, did that affect anything? So we took all the variables in the rolling of the plate and we did a predictive model. remember that just the anodizing process is where we focused the DOE. We didn't have enough, in DOEs you don't usually have enough resources to get all the variables and collect them manually in a DOE. That's a controlled study, but you don't usually have the resources to go into a lot of detail. So by mining the data end to end from a data warehouse, you can get a lot of information. So what we found out was by taking all of the data end to end, particle size. Let's go back and look and see what that is. So the particle size in the coolant, this liquid that's bathing the plate, the particle size in that emulsion was the number 2 variable contributing. When we started working with the engineers and discussing this, they said, oh my goodness, we never thought about it. But that is what really conditions the surface of the metal. And that conditioning of the surface of the metal is what is key to having the coating stick. So if that particle size starts getting larger and larger through time, it changes the surface tension on the metal and changes its ability to hold that coating. So by looking at the data end to end, we found the key variable, or as my academic friends say, it's one of those lurking variables that you don't know about. But what we were able to do is we looked at 101 variables, high variety, over 11,000 records, high volume, and we had no resource constraints looking at this data, and we actually found a key variable that we could now go back and look at. And if we wanted to do a design experiment again, we could see that we shouldn't focus just on the anodizing process, but we should focus on other areas too. So think about your processes end to end and what variables might be there that you should consider. Network diagrams. Here I'm disrupting Pareto. Sorry, Dr. Duran, but we have a new kid on the block here in network diagrams. And in this network diagram, many of you have probably seen them using network diagrams to find people or situations. This is used to look at data. So in this case, we're looking at warranty data from automobiles. And we can look at several things at the same time. If you remember when you learned about Paretos, the y-axis could have one of 3 values. It could have frequency, it could have time, or it could have dollars. And what I've seen in teaching this over the years, I've taught all 3, but we very seldom use time or dollars because the data is so hard to get. We've usually used frequency. What's happened most often, and that's what we Pareto on, is the frequency of a problem instead of what it costs to fix it, or what it costs the company, or how much time it takes away, because that data is hard to get. Well, in a data warehouse, you have a lot of that variety of data. So in this one, we did have the claim amount, we had the number of claims, we had the labor cost and the material cost. So we have the size of the node is the claim, the color's the count, and then the width and the color of the line has to do with labor and materials. So what we're looking at, the platform, we were looking at automobiles and light-duty pickup trucks, different engine types, and different model years. So now, if you watch this and think about how many Paretos would I have to do to get the same information I'm going to show you. So think about that. So first, these are passenger cars. So that's the highest frequency and the highest claim dollars. Pickup trucks, not so much. Warranty cost is less on the pickup trucks for this particular company. 8-cylinder engines had the highest claim rate and dollar amount. So now we have passenger cars with 8-cylinder engines. They're the things that are giving us the heartburn on warranty. And it's also giving us the highest labor for repairs in the warranty. Wow, look at this over here. The little tiny one is the turbo. Now, why would we want to look at the tiny one? Well, what is it they're doing right in the turbos that they're not doing in the other cars? So maybe we can learn something from what's being done in manufacturing the turbos versus the other automobiles or trucks. So now let's take this one level deeper. And we see that, 4-cylinder engines are also a culprit. as was the 8-cylinder, and it's 2008. Now, why 2008 pops out? Did we change the configuration of the car? Did we change the model? And the 4-cylinder seems to have the highest material and labor costs in warranty. There's the 2009. So it looks like we fixed something between 2008 and 2009 that improved our warranty. So what did we do, and how can we learn from that? Gee, look at this little dot down here. This little one down here is the 2006. So what is it we were doing early that had low warranty costs in 2006 that now ballooned in 2008? What was the transition between 2006 and 2008 that we can learn from and see what we can do to go back to the methodologies we were using in 2006? So I hope you can see the value of this network diagram, because if you think about, again, the number of Pareto charts you would have had to do to get dollars, counts, and time and materials, that would have been a pretty arduous task compared to what a network diagram can do for you. I've also posted this on my LinkedIn page, and there's a little more detail there on some of the things about network diagrams. Cluster analysis, traditional clustering of things. Here's a new way of looking at cluster analysis. Looks simple, doesn't it? Well, it is once you break it out. So let's take the top cluster here and break it out. And we see that it has middle age and higher education, a higher level of employment, and a pretty good salary range. It really describes a middle-aged workforce. Now, if we take the bottom one, we have lower age. We don't have as high an education level. We have less employment and lower wages, probably millennials. So now we have the ability to cluster things out if we're looking at customers or if we're looking at parts or things like that. We have a cluster analysis that actually breaks things out. This is pretty complex, but then when you stratify it out, you can get a lot of information off of the clusters that are created. Discrete event simulation. This is a system for taking your value stream maps and putting it in software. So your value stream map gives you the whole process, but if we think of a value stream map or we think of a process map, what is it? It's just a series of queues. You're putting things through a process, and it's a series of queues. So it's queuing theory. If you go back to Goldratt's book, The Goal, then what's his key that he's looking for in that book? He's looking for constraints, his theory of constraints. Where are the constraints in the process? Well, with discrete event simulation software, you can find those quantitatively. So if you look at it, basically what you're looking at is you're watching the flow of the process, and then you're estimating at the different nodes what's going on. And say, for example, in a Kaizen event, you can go out to each one of the nodes, collect data, and estimate the distribution. So are we processing through here at an exponential rate? Processing through here at a normal rate? What are the rates at which we're processing? And then we can use those distributions to simulate then in the software. So each one of these nodes here, these mini queues within the big queue of the process, then we can simulate if this is an exponential, a normal, a log normal, whatever they are. Then we can put the data through here, and we can actually see where the constraints are in the process, in the software. And it's really very valuable because you can see the combinations. And it helps you to remove non-value added steps and perform theory of constraints. The interesting thing here is, not only can you analyze the process, but if you want to change the process, instead of going out on the shop floor or the offices or whatever, and actually physically moving things around to see if it works better, you can actually do the changes in the software and look at what the process would look like by looking at the software. One of the things that I like to talk about is we all have that person on the team that comes up with the wild hair ideas. the person comes out with an idea, we all roll our eyes and go, oh man, where did that come from? But if you think about it, maybe where it came from is not that far off. How long would it take to take that wild idea, throw it in the software, and see if it has merit? So really, you have the ability to do a lot of things with discrete event simulation software where you see things working. If you've read the goal and you know about constraints, you know about Herbie. So what you're doing is you're looking to see in the value stream map, where's Herbie? Where is the constraint in the process? Where did Herbie go? Where is Herbie lurking and holding up your process? Continuous stream processing. So if you have event streams, like, for example, in utilities or in oil and gas, a lot of those areas, or if you've got healthcare, operating rooms, ICUs, those kinds of things, then you've got the ability to look at event streams and how the data is coming in. So there are two key points to event streams. The throughput, how many events per second are ingested, how many events are coming through, and how much time does it take for an event to be processed. So for example, if you're in an operating room and you're an anesthesiologist, you're watching the throughput of the data on the total body oxygen, respiration rates, heart rates. You're looking at those and you're seeing the throughput and how fast that data is coming through. What's the throughput of data on that patient? And then how long does it take for it to be processed so that I can see if I need to change the amount of anesthesia for this patient while they're on the operating table. Very key when you start looking at event streams to know what the throughput rate is and what the latency is in the measurements. So now if we look at, remember we talked about discrete and streaming data. Here are the traditional control charts that we've done. We've done these traditional control charts, an individual moving range chart, and other kinds of charts. Now with continuous stream data, we've got such high volumes of data and latency, we can actually start looking at and making adjustments and doing these analyses. Sensors have what are called tags, and the tags give you the measurements, and you can actually see random noise and a signal. So the signal to noise is like a control chart, and it gives you information, and what I call this is control charts on steroids. So you can still use the Western Electric rules, even though this data is coming through very rapidly. It's like an individual range chart on steroids, and you can do the moving range also. But the individual measures, it's like a chart on steroids. You can actually then see alerts being popped up here against the Western Electric rules. Or remember back on the decision tree where we could create new rules from interactions. You can embed those rules, and you can actually look and see signals in the noise and look at the process and see if in fact you need to make an intervention of some kind on your process. Now there's all kinds of software out there, and what I talked about earlier was you really need to get management involved on the creation of the data, the access of the data, for the analysis of the data. So there's lots of software out there to choose from. But when you're doing your software evaluation, I like to use the FLIRPS model. What's the functionality? Don't buy software that's overkill, that's more than you need. Does it work in your local language? It's how usable is it? Is it user-friendly, point and click versus having to write code? Is it continually accurate over time? What's the reliability? It's performance. Work with your IT and OT people to make sure that you're not choosing something that's a resource hog, that they're going to get upset with you and say, we're not going to use your software because it's a resource hog. And then supportability. How easy is it to get help if you need it from the software company? So the FLIRPS model, to me, gives you some good questions to ask about the software when you're evaluating it. The other piece that's very important, and you'll really impress your computer people, is you say, hey, I'd like to see the Gartner Magic Quadrant. The Gartner Magic Quadrant, Gartner company evaluates software, and they evaluate all the software. And here, for example, is some old data from an advanced analytic platform. They look at the completeness of the vision of the company and their ability to execute it for their customers. So now when you look at this, you can say, okay, here's what I need to do, IT, OT people, here's what I need to do. Let's look at the software package, where it's rated, and its ability to execute what I need. You may not need the very top one here. One of these may be good enough for you, but at least you can go through and look at the Gartner evaluation and where does it fit in their magic quadrant, and be able to talk intelligently with your IT people about what kind of software you want to look at, where it is, and what kinds of things you need. So back to the beginning, use your imagination. Take the things that I've shown you today and the ones that are important to you and you want to learn more about. I do training if you're interested. I can help you out with some of that stuff. But use your imagination and combine it with your analytics. And people on your team, you may have people that are really, really good in the analytics, but they're very narrow in their scope. You may have some people who can really get out there and get outside the box, and maybe they're not as good at the analytics. Bring them together on your team and make yourself the most useful for the organization. I don't want to see quality people left in the dust while IT and engineering takes off and could often do the wrong thing right or the right thing wrong. So that's my presentation. It looks like we have some time for questions. Or did I totally blow you away?
Thank you very much again, Jim, for your presentation. Please post your questions on the Q&A section of the WebEx tool. You can post your questions on the Q&A section of the WebEx tool, and I should remind you that you can find the recording of this webinar on ASQ Toronto section website as well as ASQ Toronto YouTube channel. All right, there is one question that has been posted. How does this analytical model work in an environment where prototyping and new concept products manufacturing are of great importance? Since the data records are not readily available and variable are to be known and subject to trial and errors in a gray.
Most of the things that I talked about are from in process as opposed to prototyping and those kinds of things. There are tools for that. The design failure and the modes, the DFMEA I talked about that you might want to do with your marketing people. What I've talked about, the analytics piece here, is more for processes and in data that's being collected for quality as opposed to prototyping. So I understand, and I've talked to people who've asked the same question when I make the presentation. Prototyping is much slower getting the data, and it doesn't bode as well for these kinds of tools, except that when you're looking at the predictive model creation and you start collecting data for the creation of a predictive model, the usage and the deployment, if you keep that in mind when you're doing your prototyping and start collecting data with those three steps in mind, and like I said with the electronic fuel injection issue, start looking forward to what data do you need to start building the model, and then getting the data in motion as you're prototyping and using that, and then what is the projection for how you would deploy that. So it's it's early steps. It's the same thought process, but it's going to take time to get more data. And I realize that, and that's a kind of a different environment.
Thank you, Jim. There is another question that has been posted. How does machine learning can improve the productivity in automotive manufacturing industry?
Well, the productivity will increase as quality improves. So when you're looking at your process, especially with discrete event simulation tool, and you start looking at where the constraints are in the process, if the constraint is being caused because of rework or inspection or things like that, you can use discrete event simulation software to then give you information about where the issue is, and then start collecting data to use some of the other tools, like a network diagram and things like that. And so how that works is, as you remove constraints, things move faster, and you get higher productivity.
Thank you. The third question is, what can we do to improve the quality of data that is collected, entered by people, and it is not reliable data? Any suggestion?
I chuckle because that is the probably most interesting question. I'm going to go on a little different point there. We had a meeting in Toronto back in 2003 on that question, and tried to put together a group of people at ASQ to address that, and it fell apart, and it's never been addressed since. So that's something ASQ, one, can help with. Number two, data quality is always an issue, and there are several ways to take care of that. One is, in the data entry system, you can actually put checks and balances in the data entry system where there are ranges or key drop-down menus or other ways that you can actually create data entry forms that will minimize the probability of an error. And if you do the text analysis, I didn't touch on this, but text can also be put into a predictive model. So if you take a sample of your data, a good sample of your data, text data, and you build a predictive model, you can find some of the key variables and use those to find out where most of the errors are occurring in your data quality issue, and then address those as to where and how you would minimize those errors. It could be with electronic form data entry that has alerts and checks. There are lots of different ways to look at that. I'd have to see the specific example that we're talking about, but yes, there are ways to minimize that, and then cleansing the data afterwards can be done with text analysis and category analysis. You can actually do a lot of correction after the data has been entered, so there's both prevention and correction that can be done with text analytics.
Thank you. The other question that is posted is, can you apply these tools in financial industry like banks?
They are being used in banks, definitely. If you look at bank transactions individually and collectively, today the financial industry is using predictive modeling on credit cards. So every credit card transaction that comes through their financial institution is being tested against a predictive model. So that's one way. You can also do it with working with accountants and auditing techniques. You can actually build predictive models to look at highlighting categories in audits. There is a large software firm that has been successful in selling their products to the United States Internal Revenue Service, and they're looking at financial records from a tax perspective. So yes, banking and finance is using these tools significantly, in the bigger banks especially.
Thank you. If there is no more questions, oh, another question that is posted, can you suggest some good software for value stream mapping analytics?
Discrete event simulation software, SAS has a product called Simulation Studio. I've used one called Simio. If you Google discrete event simulation software, you'll get quite a list. I don't want to endorse anybody, and then you get angry with me if it didn't work out right. But if you Google discrete event simulation software, you'll get a list of several, and some like Simio, you can actually get a free copy that will allow you to put a limited amount of data in and play with it. I use that for demonstrations occasionally when people ask this question. I didn't have time to do that tonight, but I've used that, and I've also used SAS's Simulation Studio. Those are the two that I've used, and I know there's others out there, and it's whatever fits your needs, but that's what I would suggest.
Thank you. You can post your questions on the Q&A section of the WebEx tool. If there is no more questions, I think we can end this event.
Well, thank you very much for inviting me. I appreciate your interest in this topic, and there are other areas along these lines that I'd be willing to share with you should you be interested.
Thank you very much again, Jim, to you too for your presentation and answering all the questions. And I should remind everybody that you can find the recording of this webinar on ASQ Toronto section website as well as ASQ Toronto YouTube channel. Thank you all for joining this webinar. Goodbye and have a good night.